So before we get started, let's look at what we did in lecture number 18. So in lecture number 18, we looked at the two-photon interference effects in the temporal degrees of freedom. And as part of that, we looked at a few examples. And first example was the Hongo-Mandel effect. And in this effect, the two entangled photons, they arrive and mix at a beam splitter. And then they go in two different directions, and then one looks at them in coincidence. Now at the beam splitter, one then moves this beam splitter, and as a function of this beam splitter displacement, one then looks at this coincidence count rate. And what we find is that as a function of this beam splitter position, the coincidence count rate has this kind of profile where there is a null in the coincidence count rate at x equal to 0. So when x is equal to 0, there is really no difference between the path length. There is no difference between the path lengths, this one and that one. So at x equal to 0, in the two entangled photons have traveled exactly the same paths before reaching the detector. And as this x is increased, then that introduces difference in the path lengths, this one and that one. And then one sees the emergence of coincidence count again. So what this null means that at x equal to 0, there is no possibility, no probability of one photon going this way or going and the other photon going this way. So the only possibility that we have at x equal to 0 is that both the photons either go this way or both the photons either go that way, and as a result we don't see any coincidence. So this effect was interpreted in that the two photons, when they arrive simultaneously at a beam splitter, then they kind of get bunched together and then go in just one direction. But then this bunching interpretation was kind of challenged in this postponed compensation experiment that was done almost 9 years after this Hongo-Mandel effect. In this experiment, there some delay was introduced in order to make sure that these two photons do not arrive at the beam splitter simultaneously. So for this experiment, people used photons with different polarization. For example, this is x polarized and this is y polarized, and then we introduce a delay d in the y polarization. Now after the beam splitter, another delay is introduced, but this is a polarization dependent delay. That means if there is a y polarized photon coming this way, then that will see no delay, but if it's an x polarized photon, then that will see a delay twice d. So as a result, this basically compensates for this delay, but after it has gone, the photons have gone through the beam splitter. And in this experiment also, as a function of this beam splitter displacement, one sees the same kind of effect that one sees in the Hongo-Mandel. But x equal to 0 in this experiment, at x equal to 0 position in this experiment, one still has this delay. X equal to 0 does not correspond to these two photons arriving simultaneously at the beam splitter. So what this experiment confirmed, that even if the entangled photons do not arrive simultaneously at the beam splitter, one can still see this Hongo-Mandel effect. So this effect is a part of the bigger picture in which we understand two-photon interference, and this bunching interpretation that was particular to this Hongo-Mandel effect is just one interpretation. It is not the generalized explanation. Another experiment we discussed in the last lecture was induced coherence experiment. Now in this experiment, one actually sees one photon interference effect in this two-photon setup. So in this experiment, a pump is split into two. The pump photon can either go this way or go that way, and as a result it can either get down converted in this crystal or in that crystal. And then if it gets down converted in this crystal, then the pump photons, so then the entangled photons can go this way or that way to the detector. And if the pump get down converted here, then the entangled photons can go like this and like that to the detector and get detected in coincidence. But in this experiment, what one saw that if one just looks at the single photon count rate at this detector, one still sees interference. This was mind-boggling in the sense that if we look at this detector and the ways in which it can get a photon, so there are two alternative ways. One is this and the other one is this. Now the path length difference between these two alternatives in a regular setup is about 15 centimeters or so. But the coherence length of these photons, these down converted photons, is of the order of 100 micron. So there is no way this experiment, this effect can be explained in terms of the first order coherence. So the way this was explained, that in these experiments, that is with these entangled photons, one photon count rate is actually given by sum of two photon count rates. And as we derived, this is coming straight from the probability theory. So what we have here is one photon count rate is sum of all the coincidence count rate between x and yi's are the locations where the other partner can actually go to. So in this experiment, if you look at the detector A, then the photon reaching detector A, its partner can only go to B. So RA is basically equal to the coincidence between AB. But if you look at the singles counted at RB, then the photon that reaches here can go there, and it can as well go to this detector, and hence the singles counted at B is equal to RAB plus RCB. And when we calculate, then we see that RA shows the interference term, but RB is just a constant. This is what we see in the experiment. So this is how we explain one photon count rates, one photon effect in two photon interference experiments. Okay, so this is all we did in last lecture. We also had an intuitive way of explaining this two photon interference, but today we are going to do two photon interference in the spatial degree of freedom. So first, let's look at the two photon state that is produced by SPDC in the spatial domain, and this is the effective interaction Hamiltonian. This is the full interaction Hamiltonian that we had derived in 2 lectures ago, and we had used the one-dimensional version of this Hamiltonian, but today we'll use the full Hamiltonian. So that's the interaction Hamiltonian. Now, before we get into the modal expansion, I just wanted to kind of remind that how we deal with the classical field. So when we have a classical field VRT, we can express that in the frequency domain by taking the Fourier transform like this. So VRT, we keep the R variable, and then from t time domain we go to the frequency domain in this manner with the I e to the I omega t. Now these are the components at the frequency omega, and this we can also write u rho z, because basically we are writing R as u rho z, and this is with the aim that we're going to expand this in a two-dimensional manner and not in a three-dimensional manner. So if we expand this in a two-dimensional manner, then this u rho z can actually be written in this form, and this we had derived. So we see that this rho, this is the two-dimensional vector, and then we go to this two-dimensional spatial frequency domain, and we can write this u rho z in this manner. And so finally this VRT we can write in this manner. So Z still remains there, but we have introduced frequency space and also the spatial frequency, two-dimensional spatial frequency space. So this is how we actually expand a classical field. Just to remind, these are the different terms, and that's what they mean. This is the K, this is the wave vector, that's a Q two-dimensional spatial frequency, Qx Qy, and the frequency is basically C times the modulus of the wave vector, and so on. So the modal expansion that we have done here, that works exactly the same way for quantum fields as well. So if we have a quantum field EP plus RT, we can do the modal expansion exactly the same. There is no difference. So here, since pump is a very intense field, we don't deal with we don't treat pump as a quantum field. We just take it as a classical field with this classical field amplitude. But the signal idler fields, we will treat them quantum mechanically, and there we just replace this classical amplitude by this quantum electric field operators, and this we had discussed earlier. So the only thing I wanted to kind of point out here is that the modal expansion works exactly the same way for classical as well as for quantum fields. Okay, so with this modal expansion, then we can substitute this EP plus, ES minus, EI minus in this Hamiltonian here, and after substituting we can see that this Hamiltonian, this interaction Hamiltonian rather, can be written in this manner. So that's the big Hamiltonian we have here. So that's the Hamiltonian, and now we want to derive the state that this Hamiltonian or this interaction produces. So again, as we had done earlier, the state of the two photon right at the beginning of this crystal, that is at psi minus t interaction, that is given by vacuum S, vacuum I. That means no photon in the signal mode, no photon in the Euler mode. So that's the vacuum S, vacuum I. And after time t interaction, then when t equal to 0, then the two photon state is given by the evolution of the Schrodinger equation. So that's the initial state psi minus t interaction, and that's the final state psi at t equal to 0, and that's the Hamiltonian we have, and this we had seen earlier as well. So this will do the perturbative expansion, and the first term is the vacuum term, and second term is the two photon term. We again know that the third term is the 4 photon term, and so on, but we'll only look at the second term in the expansion, because that is the two photon state that we are interested in. So that is the full two photon state expression that we have. Now we take this, and then of course here we have put in for dq r, we have put in this d2 rho dz. Now in this expression, just like we had done for time, we'll make some assumption. The first assumption is the interaction time T interaction that is much longer than the time scale over which down conversion takes place. So this we had again done earlier as well, and as a result this e to the I omega s plus omega I minus omega p time t, this integral can be written as this Dirac delta function, and here we are referring to this integral and these three integrals. So this can be this dt and this integral. This can be written as this delta function. Similarly, we also assume that the effective interaction area is much smaller than the actual size of the nonlinear medium. And for this we can just go back to this figure. This assumption essentially means that the size of this laser beam that is falling onto this crystal and doing the interaction, that is much smaller than the size of the transverse size of the nonlinear medium. So with that assumption, we can essentially put this rho integral, we can take the limits to minus infinity to infinity, and this way we can write this rho integral, which comes from this qp minus qs minus qi dot rho, and then this d2 rho. So this integral then we can write or approximate as the this Dirac delta function, and this is a very valid assumption in the laboratory setting, in which the size of the pump laser beam is usually much smaller than the nonlinear crystal one uses. So with these two assumptions, if we put in this expression, then we can see this second term or the two-photon state takes this form. And again here we have used phi to represent the phase matching function. So this phi is basically the phase matching function. Okay, so that is the two-photon state we have in the most generic sense. We can take two special cases of it. I mean, here we have dqs, dqi, as well as omega s, omega. So that's the most generic state, but here we can take some special cases. The case one is when signal idler directions are fixed. So when qs and qi are fixed, in that case this v qs plus qi omega s plus omega I, this takes up this form in the sense that qs can only take one value, qs 0, qi can take only one value, qi 0, and therefore this two-photon state then we can write as this with this delta function, and if we integrate that, then these two integrals go away and we can just have it as a frequency integral. And in that case we need not even show these variables, these indices qs naught and qi naught, and then two-photon state is simply given by this integral. So this is basically the two-photon state that we have derived while in the context of temporal two-photon interference. So that's the same state we have. Now we can also take the second case where the signal idler fields are actually monochromatic. So in that case, this v qs qi, this quantity can write like this, where omega s, the signal frequency, takes this single value omega s naught, that's monochromatic, omega I is the omega I naught, and then when we substitute it in here and integrate over this delta integral, we obtain this expression for the two-photon state. Here this is the phase matching function. Again, we can choose not to write the frequency arguments here, and in that case the two-photon state can simply be written like this. So that's the two-photon state when we have a monochromatic signal idler field, but qs and qi can take any value. That is a field when qs and qi are fixed, but the frequencies can take any value. So this is the two-photon state in the transverse momentum basis, and signal idler fields are monochromatic. Now let's look at a special case for this one, is when the pump field is just a plane wave. So if the pump field is a plane wave, then this v, that is the amplitude of the pump essentially, that will take just a single value of qs plus qi. So that qs plus qi, if that is, let's say, q naught, then this integral can just write as a single integral instead of this double integral. Now when we write it in this form, we can see that this integral is essentially inseparable as far as signal idler modes are concerned. We cannot write this state as a state of signal times a state of idler. So that this is basically an inseparable state and thus an entangled state. So I mean, when we have the two-dimensional integral, it's not easy to see, but when we write this as a one-dimensional integral, then it is very easy to see that this is an inseparable state. Of course, even when the pump is not a plane wave, we do have these fields being entangled, but that will prove in details later. But at this point, I just wanted to show that at least for the special case, it's easy to see that this is an inseparable state for signal idler modes, and thus it is an entangled state. Okay, so now that we have derived the two-photon state, let's look at the two-photon interference effect that one can see with these kind of states. So here is a generic two-photon interference setup. Here we have a partially coherent pump, so it need not be a fully coherent pump. It's partially coherent pump producing down conversion, so signal fields get produced. These fields then go through this screen which has these 4 apertures, 4 holes, and the experiment is arranged in such a way that the signal photons can go to these detectors in 2 different alternative ways. In the first alternative, the signal photon goes through this rho Si and idler photon goes through rho S1, idler photon goes through rho I1, and in the second alternative, signal photon goes through rho S2 and idler photon goes through rho I2. So these are the 2 alternatives that these 2 photons take in order to reach these detectors. And so the interference is basically interference between this and this alternative, and the interference will take place as long as these 2 alternatives are indistinguishable, or as long as these 2 alternatives are coherent with respect to each other. And we'll now see how to define, how to mathematically derive the condition to see as to what extent these 2 alternatives remain coherent. So in order to do that, we again introduce these terms delta rho and delta rho prime. This is just as we had done delta L and delta L prime in the other case. So delta rho is rho 1 minus rho 2, where rho 1 is just the average of this distance, which is rho S1 plus rho I1 by 2. Rho 2 is the average of these 2 distances or displacements, and that's rho S2 plus rho I2 by 2, and the difference is delta rho. Delta rho prime is rho 1 prime minus rho 2 prime, and rho 1 prime is defined as rho S1 minus rho I1, so that's this vector, and rho 2 prime as rho S2 minus rho I2, that's this vector, and their difference as delta rho prime. So this is pretty much in the same sense as we had defined delta L and delta L prime, and we'll try to see that we'll try to derive the 2-photon interference law in terms of these 2 quantities. Okay, now the coincidence count rate that we will see at this detector, and this coincidence count rate is essentially the probability per unit time square that a photon is detected at position Rs, that's position Rs at time t, and another photon at position Ri at time t plus tau. And this we have seen that this is given by this expression, where this is the 2-photon state. These are the detected efficiencies of the 2 detectors, and here we have these 4 field operators: Es minus, Ei plus, Es plus. Again, this one is the expectation value of this field operator, and the second one is the ensemble average over those expectation values when the state psi Tp is not pure, when it is mixed, and that's when we need to do a second average. Okay, so the electric field operators Es, this is the electric field operator at the signal detector, and this is the electric field operator at the idler detector. So Es plus at the signal detector we can write in terms of the electric field operators in the 2 alternatives. So this Es at Rs, this we can write as the electric field operator in the first alternative plus the electric field operator in the second alternative. We are including this one as well to take care of the temporal effects, because this may travel different, the signal can travel a different distance in alternative 1 compared to when it is in the second alternative, and so on. So this signal electric field operator is written in terms of Es1 and Es2, and the idler electric field operator is written in terms of the idler electric field operators in alternative 1 and alternative 2. Again, this is a very similar structure, mathematical structure and formalism as we did for the temporal case. So I'm pretty much repeating it over here. Now, so if we use this form of the electric field, then the coincidence count rate, this expression can be written like this, where we have just these 4 terms, and other terms will actually not show up. Now, in here for the 2-photon state, we consider signal fields to be monochromatic, and as we had just done like a few slides ago, the POM field in this case takes this form, and the 2-photon state has this form. We will simplify it a little bit more and assume that this phase matching function phi omega s naught omega I naught is actually 1. This just makes the math simpler, and then it makes it easy to kind of explain the main concept, but in general the phi need not be 1, and one can still do this. So when this is 1, then this 2-photon state simply takes this form. And then if we assume the paraxial approximation for the field, then these electric field operators, this ES1, EI1, EI2 and ES2, we can write like this. So here I have written expressions for ES1 plus, EI1 plus, and this is just the paraxial approximation. Again, the modal expansion here and then the way that we carry out the paraxial approximation is exactly the same as we do it for the classical fields. This is the electric field operators within paraxial approximation. So we assume this for the 2-photon state and the paraxial approximation for the electric field operator, and with that the coincidence count rate, we can write this expression, we can write it like this. This is just the 4 terms we have here, and that's just the 4 terms we have over here. So first term, I mean, this is the generic structure we see for any interference involving 2 alternatives. So the first term is the coincidence count rate if only alternative 1 was there. Second one is the coincidence count rate if only alternative 2 was there, and when both the alternatives are there and they are mutually coherent, then we will have these 2 extra terms as well. This K1 and K2, these are the splitting constant because of the size of the hole and so on. So that's the coincidence count rate we have over here. And this is the 2-photon interference. This is the generic 2-photon interference law, and we see the structure again is same as we have for any interference, whether it is 1 photon, 2 photon, as long as it involves 2 interfering alternatives. This is the generic structure that we have seen. Now this W2 rho S1, rho I1, rho S2, rho I2, which is defined like this. This we can actually call 2-photon cross spectral density function. This terminology is coming from 1-photon interference or the classical interference, where we call the first term was the spectral density and the cross terms we call the cross spectral density. So since this involves 2-photon, we are calling 2-photon cross spectral density function. And the S2, this we can call as 2-photon spectral density in alternative 1. For this one, similarly we have this one is a 2-photon spectral density in alternative 2. And the cross spectral density, then we can write in this manner, where we are introducing the spectral densities and this function, which is the degree of spatial 2-photon coherence. So again, this is a very generic structure that we see in classical interference involving 2 alternatives, as well as 1-photon interference involving 2 alternatives. And this quantity that shows up here, this we call the degree of spatial 2-photon coherence. So this is the generic description of 2-photon interference in the spatial degree of freedom, and we have seen that we have described it in the sense that a 2-photon interferes with itself. And then we have got the structure that we have seen throughout this course whenever there are at least 2 interfering alternatives. So we will stop here. Thank you.